Great, thank you. So I want to follow that by thinking about some of the same questions in the Brazilian Amazon, in the commercial cropland region in Mato Grosso state. And I want to sort of scale that up all the way to the watershed scale. So take that question of where nitrogen is going in soils and in crops, but look at the processes that drive the movement of nitrogen, and I'll throw phosphorus in there also, up to the watershed scale. So this is a team effort. This is the team at the Woods Hole Research Center, but we do work and have for many years with a number of marvelous scientists at the EPAM, the Environmental Research Institute in Brasilia, that's been our wonderful partner in this work for many years. So this, you heard a lot yesterday and this morning with Steph Sparrow's talk about this farming system in the Amazon and Cerrado regions of Brazil, but it really is the fruits of technology that not only developed tropical soybean varieties that could grow in the short, even day length environment and warm temperatures, but also the agronomic modifications of highly acid soils with very, very low phosphorus, native phosphorus availability. And it is those inputs that make this system possible. This is a highly mechanized system. These are just some pictures from the area where we work. This is very much a consequence of soybeans being a global commodity. So these soybeans from the middle of Mato Grosso get put on big trucks, travel on dirt roads 75 kilometers from where we work to a paved road, and then go to the ports of eastern Brazil and Sao Paulo and Paraná states. And the largest change that's happened over the last few years is that while Europe was the largest consumer of Mato Grosso soybeans in the mid-2000s, China quickly became the receiver of most of the soybeans being produced in the Amazon, and that continues today, driven by rising incomes, increasing meat consumption, and all those sort of global factors that require grains, high protein. So I'm a watershed biogeochemist. I'm interested in questions of how nutrients behave across land use transitions, and I'm also interested in the processes that drive the movement of those nutrients from land through soils into watersheds. So I want to focus on these transitions here, and that transition really started with native evergreen tropical forest. This is, I'll show you where we are in a second, but this is forest that's deep-rooted and stays green the whole year in a rainfall regime that gets about 1.8 to 2 meters of rain a year. Some of that was converted to pasture, and Steph talked about that very nicely. I'm going to skip over that transition, but then focus on the transition from forest to single crop soybeans, and then the double cropping of soybeans with maize. And the reason I, as a biogeochemist, am extremely interested in that transition is that no mineral nitrogen fertilizer is used on the soybean phase of the crop because soybean fixes nitrogen, but this phase of the cropping system, which is kind of brand new in this part of the world, uses sort of 80 to 100 kilograms of nitrogen. Not the requirements in use here, but still relatively high. So that has consequences potentially at the watershed scale. So I'm interested in those large watershed scale consequences of the use of these fertilizers. And so this is just, a map you've all seen of the Midwest and the nitrogen that moves from farmland into streams and rivers down the Mississippi and ends up causing a dead zone in the Gulf of Mexico when that nitrogen hits estuaries and coastal regions. So I'm focusing on a couple of key questions. Will the trajectories of impact follow from our understanding that's largely been developed in trying to understand temperate intensive agriculture? And if not, why not? What processes control the fate of water and nutrients in intensive Amazon commercial agriculture? So we started with this question at the watershed scale. Well, let me explain first where we work. So this team has been focusing a lot of work at the Tanguru Ranch, which is here. This is an 80,000 hectare farm. We love it because it's got half its area in crops, but half its area, so 40,000 hectares of intact tropical forest. That's a scale at which we can put whole watersheds. It lies here at the edge of the Xingu Indigenous Reserve, but in this area that Steph Sparrow was talking about, where this lots of forest to crop transition and pasture to crop, and also just sort of single crop to double cropping has occurred in this farmland region. So we're right at the edge. Here's the savanna, the cerrado. Here's the forest boundary. We're right here with this nice playground that's a real typical soybean farm. So I started with this question: how does water move from farm fields and forests into watersheds? We started by measuring infiltration rates, simply going out and putting infiltrometers and measuring rates of water infiltration into farm fields and forests in a setting like that. And we found the following thing. So here's infiltrability. This is surface infiltrability in forest compared with soybeans, right? So it goes down. This is an astounding amount of water. This soil can infiltrate more than half the annual rainfall in 1 hour. It goes down with soybeans, but it still is pretty high, right? Hundreds of millimeters per hour. This line is the maximum 5-minute rain intensity. So no matter how hard it rains, you can always infiltrate all of that rain into the soil surface in these soils, right? These are high clay soils, 30% clay, but they're aggregated, and water moves through them like sands. So you don't get the situation where you generate surface erosion generating water flows. And that's critical, and I'll show you how that translates up to the watershed. But if we go back, just as a little story, these stripes here were places where 2 years before this farm had invested millions of dollars in putting out contour berms, and it was such a pain in the neck for the tractors to drive over them that 2 years later they took them all out. And this picture has just showed where those berms used to be. They didn't need them because they never generated those erosional flows. All right, so we scale this up to the watershed. We have headwater watersheds in forest and soybean fields where 100% of the land in the watershed is in that land use. We go out into headwater streams. This is one of the very smaller ones. Measure discharge. We have gauging stations so we can relate flows stage to discharge. We measure water flow, and that allows it, and we match that with regular measurements of water chemistry to generate estimates of not only the water, how much water is leaving across the hydrologic year, but also the fluxes of nutrients out of those watersheds, right? So here's the sum in one figure of what that annual hydrograph pattern looks like. Here's the rainfall, right? Almost no rain for some months of the year, quite a bit of rain in some months. Here's stream flow in forest, right? Almost no seasonal variation. In the dry season, that stream is flowing just like it is in the wet season. Absolutely remarkable. It's those vertical flow paths make it a completely groundwater dominated system. So those flows are just regular. In the soybean fields, this is what trees do. They put water back in the atmosphere. If you take away the trees, then there's 4 times more discharge from headwater streams total over the year. They're not flashy. The average monthly discharges are in the wet season are really not that much higher. It's very different than these temperate systems where you have very little discharge in the summer when everything's transpiring and lots of discharge other times of the year. So not very flashy, but a big difference in total water yield from streams, from headwater streams. All right, so now we try to link that understanding of the watershed hydrology to the fate of nutrients, nitrogen and phosphorus. I'm going to start with the phosphorus because the story is very easy. These fields receive 50 kilograms of phosphorus per hectare. We plugged into this system after these soybean fields had been there from, say, about 6 to 11 or 12 years. We went into native forest and we measured the 2 more available forms of phosphorus. This is the extractable inorganic P. This is the sort of quite labile inorganic or organic phosphorus extracted with bicarbonate. Here's what the profiles looked like in the forest, right? Here's what they looked like in the soybeans after about 10 years. A big increase in inorganic P in the surface soils, but seriously, you cannot see any of that added P, 50 kilos per hectare, for a decade below 30 centimeters. These soils fix phosphorus so strongly that everything that they've been putting for a decade remains in the top 30 or 40 centimeters of soil, right? So how does phosphorus move into aquatic systems? By movement of particles. This system, this system does not generate erosional flows. The phosphorus, you know, if you could move this phosphorus into a stream, you would have a phosphorus problem, but you don't, right? So you can load up soils with phosphorus, and there is a tremendous capacity. These soils are very deep. They're often 20 or more meters deep before you hit any kind of parent material. So there is an awful lot of soil and an awful lot of capacity for fixation, and you can probably go on fertilizing like that for decades without ever seeing phosphorus break through to surface waters if you don't generate those erosional flows, and the system is kind of set up not to have lots of erosional flow. All right, so here's nitrogen. We did a very similar experiment modeled after the one Kate just showed you, where we went out and we fertilized fields, plots really, with different levels of nitrogen, and we measured, this is just the nitrogen, the same thing Kate did, extractable nitrogen in soil. We fertilized here. This is during the corn phase, and we see a big increase in the available nitrogen in soil when you put fertilizer. Here's the control with no fertilizer, but we greatly make nitrogen available in soil. A few days later, all the urea fertilizer nitrifies. This is, I love this kind of textbook example of nitrification. And so you're set up with this soil with all this nitrate in solution. None of it leaches down. Our lysimeters pick up 0 leaching out vertically, even though it's very available for the crop in the surface soil, right? Where does it go? Some of it makes it down. These are profiles to 8 meters. These are brand new. I think these are super cool. We see lots of nitrate stuck on soil sites down deep. That goes up under soybeans. Soybeans, we think, fix about 200 kilos of N per year. And then when you combine that with the fertilizer, you get lots of nitrate retained at these middle soil depths. So you'd never see it if you weren't looking down 4 to 8 meters. So that acts as a very big brake against nitrogen leaving through the watershed and ending up in streams. All right, water chemistry. Here's in one slide, 10 years of my life. Here's watershed scale export of nitrate and forest. So remember, 4 times more water, 4 times more nitrate. The concentration never changes. Industrial soybeans, native forest, the same concentration of nitrate in streams. It's remarkable. And a 3-fold or 3 to 4-fold difference in export based on 3 to 4-fold more water, no phosphorus leaving, very little ammonium and nitrate. Total exports of N less than about 1.5 kilos per hectare. Those are really tightly retentive systems at the watershed scale. And so that's a function of these deep soils. Almost all the double cropping expansion now is occurring on these soils. All this kind of light orange color is those soils. This is where the action is. We think this is a phenomenon that's very generalizable across this region over which this intensification is happening. So I would argue that what we know about temperate systems does not apply in a blanket way here. There's this remarkable resistance to changes to water chemistry, driven by our understanding now of high infiltration and low erosion, strongly P-fixing soils, N retention in the soil profile and little downward N leaching, low solute and sediment exports, because you're not generating erosion, you're not exporting sediment from these headwater watersheds either. But there are some things we have to think about for the future. We don't know what ultimately the capacity of those soils to retain nitrate is. Will we saturate them? Will we get breakthrough if we farm for decades like we're doing on these soils? We don't know that. Future practices may have different consequences. If we start irrigating as a hedge against climate change, that will change leaching and greenhouse gas emissions. I haven't talked about greenhouse gas emissions, but they are also quite low. As long as you stay below about 160 kilos of N application per hectare, but we don't know what those future practices will do. And I'll set up some of the afternoon or talks that the climate feedbacks that reduce rain in this rain-fed agricultural system are probably going to drive the future and sustainability of this system, perhaps before, at least under well-managed systems, the water quality impacts do. So it's a quite different system driven by the nature of deep soils and the nature of the hydrology of those systems, and the fact that the timing and the magnitude of nitrogen fertilizer particularly seem to be very well matched to the demands of the crop as it's being currently practiced. All right, thank you.